let's imagine we're floating around in space and we're right next to this cool big black hole, right? And I give you a little push.
I'm getting in.
Right? Yeah. Who's first, right? Let's see who's going to jump in.
It's fine once you're in.
Yeah. All right, so I give you a little push. What do you think might happen?
Spaghettified.
Spaghettified. So you've heard of spaghettification, right? So what's happening here now, because this bending of space-time is so steep, right? So let's say we fell in feet first, okay? Now there's an incredibly large, the difference between the amount of gravity at my feet and at my head is huge. Right now it's also different because my feet are closer to the earth than my head is, but the difference is so small it makes absolutely no effect on us, right? But in a black hole, right, once you're inside that event horizon, even as you're falling in to the event horizon, there's so much gravity now that your feet would start to get stretched out, right? They're falling in faster than your head is, so you'd be spaghettified, is the scientific term that you know, right? And you'd be stretched into this infinite long human spaghetti, okay?
Sounds great.
And then, as you're falling in, remember that radiation around the black hole? Do you remember the Hawking radiation? So basically, a black hole you can think of is like you're falling into like this wall of fire. So once you're falling in, right, you're going to get hit by all of this radiation and not be very alive, I'm guessing.
To be honest, there's very little fun to be had.
Yeah.
Black hole.
And then another part of this is so if I gave you a little push and watching you fall, actually though, when I'm looking at you, right, falling in, at some point it would look like you're just frozen there at the event horizon, not moving.
Forever.
Forever. Because because time starts to slow down. And the time slows down so much that one instant stretches on for infinity. So it's just like you're frozen in time there. And even for you there, it would just, that one instant would be frozen. That would be all of eternity.
It's a total rubbish.
Yeah.
Let's not go.
Who's jumping in first? You?
I did notice that in every example you gave, you'd given Elyes a little push.
Yeah.
I'd push him first.
And then it would be cool. If we could just send something in there and get some way of sending that information back out, it would be just incredible. Because now
it's really dark in here, and I'm a bit squashed.
Because all of our theories of physics, science, break down at that instant. So there's no way for even for us to predict what would happen. Like, no one's been near a black hole, but we're already making all these predictions of what would happen as we fell in, right? But then at some point, once you pass that event horizon, all of our science just breaks. It just doesn't work at that level because now you're in this tiny, tiny region of space with this incredible amount of gravity. And there are two theories, right, that govern these two domains. So you've got Einstein's general relativity for the gravity part, and you've got quantum mechanics for the tiny, tiny, tiny space that you're in right now. And those two don't really work well with each other. Or they give us answers when we try to put them together. They give us answers that just don't make sense. So that's one of the biggest things that areas of study that scientists are trying to work on right now, trying to put these two laws, these two theories together and get them to work.
Or it should be. Should be one of the
Yeah. So it's called
not one of the
quantum gravity is what it's called. So that's where that's a very important part of our area of study for scientists at the moment.
Anything we don't understand
is
a cool thing to study.